and welcome to our next recorded lecture. Our lecture today is on chapter 3, not a very long recording, just this short one here. We will talk about elements in this chapter. Alright, off to the chapter we go. You know the deal. Maybe a little stretching before we begin this chapter, just to make sure we're ready. Stretch and stretch. Too much stretching again. Relax. And back we go. After you.
Welcome back. We are dealing here with chapter 3 in this recording. Not a long chapter, so I think we probably knock it out here in one shot. In this chapter, we're going to talk about elements, compounds, and molecules. I know we touched upon it in an earlier chapter. We'll go back over some of that stuff. The main focus also in this chapter is going to be the periodic table. So we're going to talk about the periodic table, and we'll finish up talking a little bit about some ions and how they kind of come together. So let's get into it here. Elements, as we talked about, are really the basic building blocks of everything. As I might have used the analogy earlier on, elements are kind of like the alphabet. There's only so many elements, which, as we'll see and talked about, can be found on the periodic table. But different combinations of those elements will form different compounds. Again, just like there's only 26 letters in the alphabet, but different combinations will definitely give us different words, and they have different meanings. And kind of the same idea here, different combinations of elements that come together will give us some different compounds that have different properties as well. So elements can be naturally occurring. Most elements are naturally occurring, but they can also be synthesized in labs. So as we'll get into it, if you get sort of towards the bottomish there of the periodic table, and sometimes depending on when your periodic table is made, this sort of area-ish as well, there's a lot of sort of man-made elements that are synthesized in the lab. Remember that the smallest sort of unit of elements or representation of elements are atoms, as we talked about, and we'll get into atoms more specifically. But atoms, again, actually are made up of even smaller particles, which are sometimes referred to as subatomic particles. Again, those are particles which are protons, as we talked about previously, which are positively charged particles. They are electrons, which are negatively charged particles. And again, there are neutrons, which have no charge. But that is the basic component of pretty much any element. A basic representation of it is an atom. As we'll also talk about in a later chapter, all elements have protons, electrons, and neutrons, except for hydrogen. Hydrogen actually doesn't have a neutron, but everybody else will have protons, electrons, and neutrons. So there are about 118 elements that are known. 88 of them occur naturally, as I mentioned before. Others are sort of synthesized in the lab. At room temperature, only bromine and mercury are liquids. And also, when you look at the periodic table, you can find mercury, which is Hg, somewhere in this area-ish. And a lot of times you will find it kind of a different color on a lot of periodic tables, especially the ones that are sort of projected or put up on walls in labs or chemistry rooms. Usually will have a different color in terms of its writing to signify that they are liquids. At room temperature, there are 11 elements that are gases. We have hydrogen, nitrogen, oxygen, fluorine, chlorine, helium, neon, argon, krypton, xenon, and radon. So as you can see, obviously we have a couple that are liquids. We have some that are gases, and obviously we have some that are solids at room temperature as well. So we do have sort of a whole variety of states that we can find for our elements, but a vast majority of that 118 are going to be in the solid state under normal conditions by themselves. But again, we do have some that are gases, and again, some couple there that are liquids. 10 elements that make up pretty much 99% of the mass of the Earth. You can see there oxygen, silicon, aluminum, iron, calcium. So these are guys that make up the mass percent or most abundant of what is found on the Earth's crust, oceans, and in an atmosphere. And again, a lot of other elements, kind of a small percentage is found there. Oxygen accounts for 20% of atmosphere and is found in nearly all rocks and soil. A reminder that air, the major component of air, is actually nitrogen gas and not oxygen. It's nitrogen followed by oxygen, and then obviously other gases may be in the air depending on where you are breathing that air. But again, sometimes people think oxygen is the major component of air, but actually it's nitrogen, which sometimes surprises people. The most prevalent elements we find in the human body: oxygen, carbon, and hydrogen. Carbon, hydrogen, and oxygen, also the main components of carbohydrates, right? A little pasta maybe you're having right now, who knows? But obviously we use those as sugars as well, which is the main component of those sugars: carbons, hydrogens, and oxygens. So obviously it's not surprising that that makes up a pretty good chunk of what we find in the human body. Now, when we talk about the elements obviously have names. So each individual element will have a name, and they're also derived from a lot of different sources. They can come from Greek, Latin, or German words to describe certain properties. They could also come from historical sort of names, or places where things or elements were discovered is another very common sort of way elements are named. Also, some are named after famous scientists. Curium is an example of that. Also, we have things like Californium, which is obviously a place where it was discovered or created. A lot of the man-made or synthesized elements have some of those fun names like nobelium, einsteinium, curium. Some of these things are named for a wide variety of sources. Now, when we look at the elements, sometimes the symbols may not always be what you might think it is. Iodine, which is I, barium, which is Ba. Usually symbols will have one of two sort of ways that they are written. Either they will be one letter symbols like potassium, which is K. And if it is a one letter symbol, it is always capitalized. Some will have two letter symbols like we see there with barium, or even calcium, which is a capital C, lowercase a. If it is a two letter, first one should always be capitalized. Second one should be lowercase. And if it is a one letter symbol, the first letter and only letter should always be capitalized. Now, is that important? If you're somebody that writes like capital letters for everything, you really don't want to do that when you're writing symbols and doing chemistry. For example, if we take capital C and lowercase o, or capital O, C and capital O in this case, you may go, oh, they are the same. And they're not. Capital C, lowercase o is cobalt, the element. Capital C, capital O is carbon monoxide. So those are two very different things. And although you may be wanting to write the formula for cobalt and you write capital C, capital O, you write carbon monoxide, you're actually writing something that is very, very different. So very important, especially when you're writing these symbols, that you do not capitalize both of them, especially if it's a two letter. First one's capitalized, second one not. As we come down here, N, which we find on the periodic table, is nitrogen. AU is gold. Some other symbols that maybe you might not think of. AG is silver. Iron is actually Fe. K, which is our potassium. Lead, which is Pb. Let's see here. Copper, which is sometimes confused by people, is Cu, is copper. Only capital C is carbon. Sodium, another one that doesn't really sound like its name, is Na. And, so when you go through some of these elements, obviously we saw earlier Hg, which is mercury. That's another one that sometimes gets people. It's a really good idea at this point, and probably as soon as possible, that you get some recognition, some understanding of the symbols for these elements and the names that go along with it. You are responsible for that. It will also help you immensely when we get into the chapter where we talk about naming. And obviously, we need to use the symbols and we need to name things correctly. So there's a lot of rules about how to name certain compounds. So if you're still struggling with, what is the symbol for sodium at that point, it's going to make it twice as hard for you. So as soon as possible, you should probably get some familiarity with the symbols and the names that go along with them. When you kind of look at the periodic table, the first couple rows there or columns is a good idea to know. There's usually like a staircase that comes down, usually those guys. Kind of the top part are ones that we use a lot. Not too much using in the sort of bottomish middle of the periodic table. A couple down here on the 2 rows on the bottom in terms of elements we talk about, but not too much going on usually in those cases as well. So kind of if you look at the main part of the periodic table, kind of the left, kind of the right, and upper middle is usually really good to make sure that you understand the symbols and the elements that kind of go with them. Here's some of the elements here from your book. We have aluminum, which is Al. We have cadmium, which is Cd. We have bromine. Here's some more, obviously. And again, the familiarity with the ones that we see here and it's on the periodic table is a really good idea. These are all, I think, alphabetical order here. We have some zinc here are some of the symbols that we have going on. Continuing on here, some of the ones here are derived from earlier names. So again, they maybe don't follow as closely the pattern as you might think. I think we covered most of them on this list. This is antimony, which is SB. And we have obviously our sodium. Our tin is another one that commonly people miss. At the end, tin is SN in this case. As we talked about, again, first letter capitalized. And if it's a 2-letter, first one capitalized, second one is not, so it should be lowercase. Again, as I mentioned before, our cobalt and carbon monoxide example, writing CO would represent carbon monoxide versus cobalt, and clearly very different things as we talked about. Now, a compound is, as we talked about also earlier, remember, just a review as we're talking about through here officially in this chapter, a molecule, right, is that general definition of 2 or more atoms that are together. And remember that it could be 2 or more of the same atoms. Excuse me. It could be 2 or more of the same atoms of the same element, I guess is what I was trying to say there. It could also be 2 or more atoms of different elements together. So the molecule sort of definition, if you remember, is sort of a basic definition of all you have to meet the definition of a molecule is 2 or more atoms that come together. It can be the same element, can be different elements. They could be considered molecules. A compound, on the other hand, as we talked about, is a substance that contains 2 or more elements, right? So 2 or more atoms of different elements, and that is the main difference there. They got to be 2 or more different elements that are present. Water, again, is a compound, as it contains obviously hydrogen and oxygen elements or compounds. It contains hydrogen or oxygen atoms. It is also a molecule because it does contain a total of 3 atoms in this case. So that's the basic definition as well. It is, again, not an element. So water is not an element because obviously it contains 2 different elements. Compounds can be broken down into simpler means by chemical change. So if we run an electrical current over the water, it will break it back down into its oxygen gas and hydrogen gas in this case. And these are elements. And again, this is basically as far back as we can go. So again, these are elements, and again, that is far back as they could go. Remember that both of these elements are also what are referred to as diatomic molecules. They contain also two atoms that are present, which means that they meet that definition of a molecule as well. Elements and compounds are always combined in whole number ratio. Also very different, as we might have talked about before, but the sort of characteristics or properties of the elements are very different usually than the compounds that they make up. For example, hydrogen gas and oxygen gas have very, very different properties than when they come together to make water, which has very different properties in those two gases. Same thing with like something like sodium and chlorine. Sodium, which is a metal, and chlorine, which is a toxic green gas. When they come together, they make sodium chloride, and that is like salt, for example, which has very, very different property than obviously the sodium metal or the chlorine. You wouldn't want to put any of those things on your fries, but maybe some salt you might want to put on your fries. So very, very different properties. So the elements usually have very, very different properties than the compounds that they make when they come together through chemistry here. So when we talk about compounds, they do fall into general types. There are molecular or ionic compounds, and we'll talk a lot about these type of compounds as we go through some different chapters. But just to give you the general idea of what is the difference between these two things, molecular compounds are in a lot of cases when two nonmetals or more kind of come together. That's usually when nonmetals come together, and usually how they're kept together is through sharing of electrons. So ionic compounds are usually the combination of a nonmetal and a metal. I guess the better way of rating that would have been a metal and a nonmetal. And really, they're actually held together by no sharing of electrons. They're actually held together by what are referred to as ions. And there's positively charged ions and negatively charged ions. And it is that electrostatic attraction that holds them together. So it's kind of opposites attract. And that's what we see here. There's our water, which is a molecular compound. It is held together by sharing of electrons. Covalent bonding is referred to. And this is our sodium chloride, which is ionic, and it's held together by what's referred to as an ionic bond, which is essentially no sharing of electrons, but this, as we see down here, opposites attract. So molecular compounds held together by that covalent bonding, and as we talked about here, our ionic guy is held together by that opposites attract. That is what is referred to as an intramolecular force. It is probably one of the strongest forces you could have, which is a positive and negative attraction that come together. They also sort of arrange themselves in sort of three-dimensional space a little bit differently. Here's our water coming together. Ionic solids are basically arranged in these really ordered patterns, as you can see there, where the positive ions and negative ions come together. And they come together in a way that maximizes the attractive forces between the positive ion and the negative ion and minimizes the idea of positive and negatives being, or positive and positives being near each other and negatives sort of charges being near each other. No matter what you do in either situation, the water or the sodium chloride. Water, for example, actually is a polar compound, which means part of the water molecule is more negative and part is more positive. So there's always going to be positives and positives near each other and negatives near each other. But when they come together in a sort of a solid state, what they really try to do is keep moving around until they maximize, I got positive, negatives things near each other, and really minimize areas where you're going to have negative and negative parts of molecules or atoms near each other, and negative and negative parts near each other. Molecules, as we talked about once again, are really just that basic idea of two or more atoms together. A molecule cannot be further divided without destroying its identity. And again, some type of chemical change would be needed for that. Talk a little bit about formulas of compounds. There are some rules to writing formulas of compounds. Each atom is represented by its chemical symbol. The number of each type of atom is indicated by a subscript that's written to the right of the symbol. So when we look at H2O, this 2 goes to the hydrogen, which means we have basically 2 atoms of hydrogen. In chemistry, most of the time we do not write 1. So if you see nothing written there, it actually is assumed to be 1. And that would also go to the oxygen. So we would have 2 hydrogen atoms and 1 oxygen atom here. Same thing here for CO2, carbon dioxide, nothing written, which means 1 carbon atom. And the 2 here would go to the oxygen, so 2 oxygens. And lastly, NH3, which is ammonia. Once again, 1 nitrogen and 3 hydrogen atoms basically are present. We always have whole numbers. So these guys on the bottom, when you look at formulas, should always be whole numbers. A compound, again, always contains the same relative number of atoms in each element. So regardless of where you get your water, how much you spent for your water, it is still fundamentally H2O, which means it has 2 hydrogen atoms and 1 oxygen atom. So a chemical formula expresses the type of atoms and the number of atoms that are present. And again, we always use those subscripts, no superscripts, no big numbers in between or anything like that. Just the smallest subscript, again, to the right of the element symbol tells you how many that you have. So again, here we look at something like H2SO4, which is sulfuric acid. And that's how you would say it, H2SO4, basically. And basically, if we look at this formula here, we got 2 hydrogen atoms, 1 sulfur atom, and 4 oxygen atoms that are present in this particular case. If we take a look at something like this, this is actually what is known as calcium nitrate. And sometimes when we have what's in the parentheses here, this is calcium nitrate. Nitrate is what is referred to as a polyatomic ion. It actually is a ion that has a charge. It stays together as a unit. But if we were just really to kind of take an accounting of everything we got going on in here, we do have some parentheses happening. So we still will do the same thing. That is 1 calcium present. We do have to multiply this 2 into everybody that is here. So basically the nitrogen has 1, and 1 times 2 is 2 nitrogens. So just to super zoom in on that part of it. Again, nothing is written here, which means that's basically 1 nitrogen. So 2 times 1 is our 2 nitrogens, and our 2 times 3 would give us our 6 oxygen in this case. So this guy is made up of 1 calcium, 2 nitrogens, and 6 oxygens. And that's really because, as you see here, we have 2 of these NO3 units. So this is an ionic compound. And the calcium actually has a +2 charge. The nitrate all together has a -1 charge, and those 3 oxygens and 1 nitrogen stay together, and the overall thing actually has a -1 charge for each of them. So if we just do the addition here, that is 3 and 3 is our 6 oxygens, and 2 nitrogens is again why we get that. By the way, it also balances out. Formulas should not have charges if they are ionic compounds. That is +2, -1, and -1. So that's like a -2, +2 situation. When we put it together and we write the formula for this ionic compound, there is no overall charge. It basically equals 0. And we'll talk a little bit more about that later on here in this chapter. All right, so for each of these, why don't you take a moment and figure out how many elements of each of these things that we have. Okay, so here looking at K3PO4. That, by the way, is potassium phosphate. We take 3 for our potassium, so we got 3 potassiums. There's nothing written here, which means we have 1 phosphorus and 4 oxygens in this case. Although it looks like 40, but 4 oxygens. Here we have MgOH2, and that is magnesium hydroxide is the actual name of it. Here again, if we look at it, we got 1 magnesium. Once again, we do need to distribute this 2 into the parentheses for both of them. That would give us 2 oxygens and 2 hydrogens. And that's because the OH here is a polyatomic ion that has the form of OH minus. And 2 of them means you have 2 of those guys. So if we add them up, 2 oxygens and 2 hydrogens is basically what's happening there. As you might be able to figure out, this is -2. Magnesium actually has a +2 charge in this case. So again, you want to make sure you distribute in there if you do have parentheses to count up the correct number of atoms. All right, so for each of these, why don't you come up with the correct chemical formula and see what you end up with. Okay, so we're just going to read it here. A molecule has 6 carbon atoms, so that's a C, which is carbon, and a 6 on the bottom right of it has 6 hydrogen atoms, so that's an H, and once again, a 6 to the right there. A compound that contains half as many calcium atoms as chlorine atoms. So calcium is Ca, and chlorine is Cl. And calcium containing half as many chlorines. So if I started with 2 chlorines, half of 2 would be 1, and we would end up with CaCl2. A compound that has equal numbers of sodium and nitrogen, so 1 sodium, 1 nitrogen, and 3 times as many oxygen, so O3. And that would give us sodium nitrate, actually, in this case. So once again, subscript to the right of our symbols in each of these cases. Now, a particular compound, as I mentioned, always contains the same elements in the same proportions by mass, no matter what the origin is. So that is what's sometimes referred to as the law of definite composition. It states that compounds always contain 2 or more elements chemically combined in defined portions. And here we can see the percentage of each of these elements from water, and that's hydrogen peroxide there on the right. A reminder that we could figure out the percentages basically by taking the mass of the entire compound and just the mass of the hydrogen, and that versus the mass of the entire compound. So if we take the mass, for example, of the hydrogen divided by the mass of H2O and times it by 100%, that is again how we get to this kind of guy. But basically 2 hydrogens, 1 oxygen, 2 hydrogens, 2 oxygen in this case. The law of multiple proportions states that atoms of 2 or more elements may combine in different ratios to produce more than one compound. So here's a table of a bunch of different combinations of copper, say, and chloride or chlorine, carbon and hydrogen coming together, carbon, hydrogen, and oxygen coming together, and their different percentages. Remember, as we talked about, a law is a summary of observed behavior. A theory, right, is a model that tries to attempt to explain an observed behavior. Remember that the difference between laws and theories is a theory can be sort of revisited, may be found to be correct or not correct in all cases, but a law should always be correct. And basically how atoms can come together are the whole number proportions of their masses. Let's talk then a little bit about the introduction to the periodic table, or the periodic table itself. There is our periodic table and a couple of parts of this periodic table. Periodic table is basically an arrangement of all the elements that are present, gives a good amount of information about some different elements. When we look at the periodic table, it is broken up a couple different ways. We look at what is referred to as columns on the periodic table. Those are what are referred to as groups. If you're old like me, not too many people use families these days. Most people use groups. And if you look at a periodic table, you'll see a number of different numberings. That's a lot of numbers in one sentence. So here, if we look at it, we got just straight up 1, 2, all the way down to 18. If we take the top numbering, there's also A numbering here, which goes 1, 2, skip, 3, 4, 5, 6, 7, 8A. Some periodic tables, you might even see some B numbering in this area here. For our class and pretty much every chemistry class that you take, we use the representative numbering for the groups. And that means that when we look at the periodic table and we go to number them, we use group 1, which is here. We use the A numbering, which is group 2. We skip the middle. Group 3 is here. Group 4, group 5, group 6, group 7, and group 8. I would say probably most people leave the A off of it, but it's implied that it is the A. So when somebody says group 5, they're really talking about 5A over here and not group 5 over here. So most people don't usually say the A part of it, but it's usually what they're talking about. So we do use the A numbering or the representative numbering for our groups, which is, again, looking at it, group 1, group 2, group 3, group 4, group 5, group 6, group 7, and group 8. Now, there's also going left to right on the periodic table across a row. That is what is referred to as a period. And there's several periods on the periodic table, 1, 2, 3, 4, 5, 6, and 7. And they are headed in this direction. You go across. And that's a period on the periodic table. The number that we see above the symbol, so for example, right there, we'll take our iron and we see 26 written. That is what is known as the atomic number. And the atomic number, as we'll talk about, is the number of protons in an atom. And as you can see, one of the nice things about atomic number, if you look at the numbers all across the periodic table, there's not one number that repeats. So every individual element has its own atomic number, which means if you know how many protons there are, or you know the atomic number, you can use the periodic table to figure out what element you are talking about. Or if you know the element, you can know automatically by just finding that number on top how many protons that particular atom would have, or that element would have. The periodic table is also broken up by categories. There are metals, non-metals, and metalloids. Most periodic tables, as you can kind of see on this one as well, has what is sometimes referred to as a staircase sort of coming down. And that staircase is sort of our dividing line. To the left here of the staircase, those are metals. To the upper right here of the staircase, those are non-metals. And on the staircase, those are metalloids. This way is non-metals. And over here again, and also down here, that's all metals on this side of the periodic table. Some properties of metals. Metals are good conductors of heat and electricity. They also are malleable. They can be hammered into sheets. They can be pulled into wires. They typically have a shiny appearance, and all of them are pretty much solids at room temperature, except for our friend mercury that we talked about previously, which again is a liquid at room temperature. Non-metals, as you might expect, have pretty much the opposite sort of characteristic. They're poor conductors of heat and electricity. They have a more varied sort of physical property as well. They're dull, they're brittle, they're insulators. Some of our non-metals are gases like nitrogen, oxygen, chlorine. Some are liquid like bromine, and some are solids like carbon and sulfur in this case. On the staircase, that is where we have our metalloids, our semi-metals, and starting with boron, and why it's called the staircase, kind of like it's coming down. Those are going to be our semi-metals. So what are semi-metals or metalloids? Well, they're kind of between metals and non-metals, which means semi-metals or metalloids have properties that fall. Some properties are very much like metals, and some of the properties are very much like non-metals. That's why they're semiconductors. Sometimes they're found in there because, you know, they have some characteristics that you would say, oh, that's a metal characteristic. And that same element will have some characteristics that you would say, oh, that looks like a non-metal sort of characteristic. So as you can see, their placement on the periodic table is pretty much in a nice location. It's kind of that transitioning point between metals to non-metals. Now, some groups do have special names, and you do need to be aware of it. Starting in group 1, which is over here, this is the alkali metals. And very important distinction is, although pretty much on every single periodic table you have, you will find hydrogen there. And hydrogen is actually not part of group 1. So group 1 actually starts with lithium. And why is hydrogen not part of group 1? Well, I threw a highlighter on there, which wasn't very good. But if we get rid of the highlighter there, we can see that actually hydrogen, which is found here on the left-hand side of the periodic table, is a non-metal. And it is not a metal. So although it is found on the left-hand side of the periodic table, and the reason for that is it has some special properties, and sometimes it acts like a metal, but it's actually a non-metal. Years ago, they actually would find on periodic tables, they would actually throw hydrogen on both sides. You would not very commonly find hydrogen over there on the left and right-hand side of the periodic table. But nowadays, you just put them over there on the left, but because it's a non-metal, it is not part of group 1 and not part of the alkali metals, which again starts with lithium. Right next door is group number 2, which is our alkaline earth metals. Group 1 and group 2 are called alkaline earth metals and alkali metals. And the word alkaline means basic. And most of our strong bases actually come from group 1 and group 2 on the periodic table. That's where a lot of strong bases come from, which is hence their name. Over there where I scribbled hydrogen in, I'll get rid of it here. There we go. Group 7 are our halogens. That's our fluorine, our chlorine, our bromine, our iodine. Those are a lot of those diatomic molecules. So looking at our halogens here, they are very reactive nonmetals. They also will form a lot of acids like hydrofluoric acid, hydrochloric acid, hydrobromic acid when they combine with hydrogen. But as you can see, there are a lot of diatomic molecules. Most of them are gases. So we got a yellow gas, a green gas, kind of like a liquid with some vapor over it, and a purple solid is our iodine. Group 8 on the periodic table is our noble gases, and group 8, which is over here, are noble gases. Noble means rare, and a set apart, which means that they are very unreactive. They don't like to react with others. They will react with themselves, but basically not other things. 2 rows on the bottom are set aside to not make the periodic table look too big. We'll take a look at those in just a second on the next slide where we actually see the numbering. But there are 2 rows on the bottom here that didn't get onto this picture. Let's then look at the transition metal. Transition metals are found between groups 2 and group 3. That is our transition metals. And as we'll talk about, some of the characteristics transition metals are, they are metals, but they can make a varied type of positive charge. So for example, copper can be +1 or +2. Iron can be +2 or +3, depending on the situation. So that's one of the characteristics of transition metals is they can make multiple types of charges, as we'll talk about in a later chapter. Speaking about the 2 bottom rows here, these 2 rows, if you follow the numbering on the periodic table, the atomic numbering, that's 56, that's 57, that's 72. Actually, this 58 row should go right about there. And if you go below it, 89, 104, 90 should go right about here. So those 2 rows on the bottom here technically would go right into that spot on the periodic table. And usually they don't do that. Otherwise, your periodic table is super wide. They're also called, and we get rid of some of my scribbling here. They're also called the lanthanide and actinide series because those are the 2 elements that they technically should follow on the periodic table. So these 2 rows on the bottom are also sometimes referred to as intertransition metals because, again, these are our transition metals here. And technically speaking, these 2 guys should go into here. So they're sometimes referred to as intertransition metals. The characteristic shape of the periodic table was devised to place elements that are related to one another near each other. And they did a good job. They sort of spaced out, left room, and put things that have very similar properties near each other. So elements that belong to the same group typically will have very similar chemical type properties. As you move across from left to right on the periodic table, you're going from a more metal to non-metal sort of transition as you move left to right on that periodic table. So for the periodic table, you need to know where metals, non-metals, and metalloids are. You need to know some characteristics of each of those things. You need to know how we number groups 1, 2, 3, 4, 5, 6, 7, 8. You need to know periods. You need to know the names of those special groups, where the alkali metals are, alkaline earth metals, the halogens, and the noble gases are located. Now, talking about some of the more parts of our periodic table here, noble, as we talked about, are really a class set apart. In addition to group A, which is our noble gases, which really don't combine with other things, they're sometimes referred to as being chemically inert. There are actually some metals that are unreactive as well, are pretty much unreactive. Gold, silver, and platinum are pretty much unreactive. That is this group right here, or this little spot right there on the periodic table. That is our gold, silver, and platinum, which are what is sometimes referred to as noble metals there. So I'll highlight it that way, might be better. So looking a little bit more into our noble gases, which is group 8, we have all of our ons, if you will: helium, neon, argon, krypton, xenon, radon. They're colorless gases at room temperature. They're actually monoatomic, which means they do come as ones, unlike oxygen gas or hydrogen or nitrogen, which comes as twos, like O2, N2, H2, which are diatomic molecules. These are monoatomic. They do come as one. Again, very non-reactive, as we'll talk about when we talk about bonding and electrons. They're essentially what everybody tries to be like in terms of their electrons, because they're so stable. Everybody tries to get like a noble gas as they kind of go through their electrons. We talked about our noble metals there, our silver, gold, and platinum. Now, we've touched upon it before that sometimes elements can be diatomic molecules, and diatomic means basically two atoms is basically what that means. And oxygen, nitrogen gas are examples of that. Again, like I just mentioned, He is what is sometimes referred to as being monoatomic, which means one atom, basically. Here are 7 elements, as I think we talked about in that earlier chapter, but just to remind you, these are all, again, molecules, diatomic molecules: hydrogen, nitrogen, oxygen, fluorine, chlorine, and bromine and iodine. They are also, again, diatomic elements, but they are not compounds. Diatomic elements can be separated. In water, neither hydrogen and oxygen are diatomic, so they can come apart. And when they come apart, for example, to make water, we get oxygen and hydrogen together, and oxygen and hydrogen that comes together. In this case, this hydrogen is just one hydrogen sharing electrons with oxygen, as we might have talked about earlier. And same thing on the other side. It's no longer H2 like it is when it is in this gas form and a diatomic element. A reminder as well, we talked about diatomic molecules. Diatomic molecules that are elements are H2, O2, N2, and so forth. But a diatomic molecule can be two different elements together as well. So, for example, carbon monoxide, as we talked about earlier, that is a diatomic molecule. It is also a compound, but once again, it is not an element. But it's still considered a diatomic molecule. Once again, our H2 is a diatomic molecule. It is an element, but it is not a compound. And again, because it only contains, obviously, hydrogen atoms. All right, so sort of finish up on, we're going to talk a little bit about ions. Ions are atoms that basically have charges. And there's really 2 types of ions that we do come across. There are cations, which have positively charged entities, and there are anions, which basically have negatively charged entities. So how do we get those things? If we have something like sodium, for example, sodium has 11 protons, and again, protons are positively charged. And in a neutral sodium atom, we would have 11 electrons, which are negatively charged. 11 positive things and 11 negative things gives us no charge, which is what we see here. By the way, neutrons, which also sodium has, has no charge. So neutrons are neutral particles, so they don't really play into at all in terms of ions. It's really just protons and electrons. Now, when we have sodium that has a +1 charge, sodium still has 11 protons. You might be saying, how do I know it still has 11 protons? Well, we could actually go back here, go back a little bit here to, where's our periodic table there? To our periodic table discussion. And if you remember, when we look at the top number here, which is our atomic number, right? which is the number of protons that each of these elements have. There is no atomic number that repeats. And that means that if you want to know what element you have in front of you, it is the protons that determine basically what element you are dealing with. So when we go to number 11 here, it is only sodium on the entire periodic table that has the number 11. So that is how we always know that it is going to be 11 protons for sodium, by looking at the atomic number on the periodic table, as each element has its own individual atomic number, and every element has a different number of protons. So getting back to sodium with a +1 charge, in order for this to still be sodium, it's got to have those 11 protons. It cannot have anything else. That means that sodium with a +1 charge will still have 11 protons, which are positive, because it's still got to be sodium. But in this case, it actually only has 10 electrons. So 11 positive charges and 10 negative charges leaves you a +1 overall charge. And that is where the charge on sodium comes from. And this is what is known as an ion. And that's what we see here. Sodium with no charge becomes sodium with a +1 charge and gives off an electron here in this case. And this is what is referred to as a cation. If we look at magnesium, magnesium with no charge is number 12 on the periodic table, has 12 protons, which are positive, and it has to have 12 electrons, which are negative, which gives you no charge, which is what we see here. Magnesium, when it forms a charge, will form a +2 charge. Once again, magnesium's atomic number is 12, which means in order for it to still be magnesium, it's got to still have 12 protons. That's its atomic number. That means it actually has 10 electrons in this case, and that gives us a +2 charge overall, and that is where the charge comes from. Same thing with aluminum. Aluminum will have 13 electrons and 13 protons. But when it loses 3 electrons, aluminum will make a +3 charge, which means it has 13 protons, which are positively charged, and only 10 electrons, which are negatively charged, gives you that +3 overall charge that's happening here. So these are already referred to as cations, and cations are made by losing electrons. Cations. And we see that, right? If we look at sodium with no charge, 11 electrons. Sodium with +1 charge has 10 electrons. Magnesium with no charge, 12 electrons. Magnesium with a +2 charge is 10 electrons. So when you see a charge that is positive, the positive should tell you that it has lost electrons. So positive charge means it has lost electrons. And the number is actually how many electrons it lost from the neutral element. So +1 charge means it has 1 less electron than the neutral guy. +2 charge means it has 2 less electrons than the neutral guy. So positive means cation, and it has lost electrons, and the number of electrons it lost from its neutral self is equal to the actual number that you see. How do we name ions? It's very simple. We actually just use the whole name of it. So something like Na+, that would be the sodium, and then we just put ion at the end of it. Now, anions are negatively charged ions, and negatively charged ions are created by gaining electrons. And let's see how that works. So if we look at chlorine on the periodic table, it is number 17. That means that a neutral chlorine atom will have 17 protons from its atomic number on top. It would then have an equal number of negatively charged electrons, which gives us a 0 charge. Chlorine will make a -1 charge. In order for it to still be chlorine, it's got to still have the same atomic number and number of protons, which is 17. In this case, it actually will have 18 electrons. 17 positives, 18 negatives gives me a -1 overall charge. And that is where the -1 comes from. If we look at something like oxygen, and if we look at oxygen on the periodic table, oxygen is number 8 on the periodic table. And that means that oxygen with no charge will have 8 protons. And it will have a matching number of electrons, which gives us no charge. Oxygen, when it forms a charge, has a -2 charge. It will still have 8 protons because, again, on the periodic table, that is the atomic number that we see. It will have actually 10 electrons in this case. 8 positives and 10 negatives leaves us a -2 overall charge, which is where the charge comes from. So anions are formed by gaining electrons. It works kind of the same way. The negative tells you that it has gained electrons, and the number tells you how many. So -1 means it has 1 more electron than what it started with. -2 means it has gained electrons and it has 2 more electrons than what it started with. So anions gain electrons, end up with the same number of electrons gained as its charge. How do we name these guys? Actually, anions end with IDE instead of the element name. So oxygen becomes the oxide ion, IDE. Chlorine becomes the chloride, IDE ion. So negatively charged guys kind of gets the IDE ending. Kind of take out the last part of the element name, sometimes a little bit more than the last part, and just put it with IDE. So if we look at the periodic table, there are certain things that have sort of charges or fixed charges on the periodic table. Here are some of them. Everybody in group 1 will form a +1 charge. Everybody in group 2 will form a +2 charge. For the most part, group 3, it's aluminum +3. Then actually going backwards here, if you remember, our staircase kind of comes through here. Our non-metals we're talking about will be -3 for our group 5, -2 for our group 6, and these are the non-metals, and -1 there for our group 7. Most of the time, the transition metals here will have a variety of charges, but there are 3 exceptions in the transition metal region that actually have fixed charges. For example, zinc and cadmium, which are right about here. These guys will always make a +2 charge. And if you hang a left there at cadmium, you'll be at silver. Silver will make a +1 charge. So these are sort of fixed charges on the periodic table. A very good reminder, and we'll talk about a number of places, but if you take any element off the periodic table by itself, uncombined, not combined with anything else, just the way it naturally comes, they actually don't have charges. So elements on the periodic table, specifically metals and non-metals, only really gain charges when they come together. So when a non-metal and a metal come together, or a metal and a non-metal come together, that's when they gain charges. If you have just, say, silver metal by itself, it has no charge. If you have silver that's combined with a non-metal, like say in silver chloride, the silver in that case has a +1 charge. But silver by itself has no charge. Same thing with sodium. If you have sodium metal by itself, it has no charge. But if you combine sodium, say, with chlorine and make sodium chloride, then they both have charges. The sodium has a +1 charge, and the chlorine or chloride in that case would have a -1 charge. So uncombined elements do not have charges. They only gain charges when they hook up with kind of metals and non-metals. That's a good thing to kind of keep in mind. Now, compounds that contain ions are what are sometimes referred to as electrolytes. They are things that can basically conduct electricity. So most common pure substances are very poor conductors of electricity, with the exceptions of metals and graphite. Water, for example, is a bad conductor or a poor conductor of electricity. And when we're talking about water, we're talking about pure water. So pure water just H2O, nothing else in there is actually a bad conductor of electricity. What makes water that we think of or use in normal situations a good conductor of electricity is they actually contain electrolytes. They contain ions, and electrolytes are solutions that when they go into solution will break apart into ions and produce positive and negatively charged ions floating around in that solution. So, for example, when you take pure water out of the sink or in your shower, they actually put ions in there to clean it. And there's a lot of ions floating around there. And that's why water that comes out of the tap will conduct electricity and you will electrocute yourself. So don't do anything dumb. You might blow dry your hair in the shower or something like that, because you will get electrocuted. But if you have pure water, nothing in there, no ions present, it's actually a bad conductor of electricity. But, again, coming out of your faucet, not pure water for sure. When we do have ions dissolved in water, those are what are referred to as electrolyte. And it's really the presence of these ions in these solutions, these positive ions, negative ions, which help kind of complete the circuit and help it conduct electricity. So here's a couple of examples here. Substances that contain ions are sometimes referred to, a lot of ions are strong electrolytes. So as you can see here, light bulb goes off very, very brightly, conducts electricity really, really well. If you have something that's a non-electrolyte, like sugar, for example, in water, sugar is a covalent compound. It doesn't create ions, but will dissolve, is a non-electrolyte, and the light bulb will not go off. And here's our pure water example. Once again, not the water coming out of your tap, but pure water has no ions in it and will not conduct electricity. Speaking of ions, when compounds form between a metal and a non-metal, we form an ionic compound. And when they come together in sort of the solid state, they do arrange themselves in a way that maximizes, as we talked about earlier, the positive and negative guys being near each other, and minimizes the positive ions being near each other, and the negative and negative ions being near each other, right? But even in this case, you could kind of see, as best as you can do, you're going to get some negative and negative guys near each other. You're going to get some positive and positive guys near each other. But it will try to really maximize that attractive force, which is between the positive ions and the negative ions, and minimize our repulsive forces. This is ionic solid, which is sometimes referred to as a crystalline solid, and has a lot of order and long range order. For example, you could take just a portion of this and recreate this solid very easily because it's repeatable, sort of the pattern. By the way, when we look at this picture, the negative ion, which is our anion, and the positive ion, which is our cation, is smaller than each other. One is smaller, one is larger. Why is that? Well, we have a neutral atom. So a neutral atom, that's what the N stands for here. Go neutral. When it loses electrons, right? It has electrons on the outside, kind of flying around crazily. When it loses electrons, it actually becomes smaller than the original. That's because it lost a lot of its electrons. So all that electron cloud got smaller. The overall size of the cation is typically smaller than the neutral atom. So the cation is typically smaller. And that's opposite of what happens with our anion. When our neutral guy gains electrons come in, it gains electrons, and the electron cloud kind of expands, and it actually becomes larger than our neutral atom. So that's why in this picture, the anion is drawn as a bigger circle than the cation, which is the smallest circle, because the cation has lost electrons. The anion has gained electrons and become larger because of its electron cloud has just sort of got larger. The cation lost those electrons, electron cloud starts to shrink. So a chemical compound that involves ions, which are really ionic compounds, should be basically balanced out in terms of their charge. So whenever we have an ionic compound, which you could recognize it by basically, if you see a metal and a non-metal has come together, check, happy phase. That is definitely going to be an ionic compound. So sodium, which is group 1 on the periodic table, is really a +1 charge. Chlorine, which is group 7 on the periodic table, has a -1 charge. So when we put these together, we want to equal 0. So +1 and -1 means we just need one of each of these, and that will give us sodium chloride here. By the way, although this is written with no overall charge, it is made up of a cation, which is the sodium ion, and an anion, which is the chloride ion in this case. When we look at calcium, calcium is +2. And that's group number 2 on the periodic table. Chlorine, group 7 on the periodic table, which is chlorine. If we were to throw these guys together exactly the way it is, just one of each of them, we would end up with CaCl, and we would actually end up with a +1 overall charge, because that's +1 and -1 gives us a +1 charge. That is no good. We need to make sure that we have no overall charge. It equals 0. So we actually would need one more chloride there to balance it out. So in this case, we would need 1 calcium and not 1, but 2 chlorides to give us a -2 to balance out the +2. And we would get our CaCl2 formula. So why don't you take a moment here and try these here, put these together in a proper ionic compound formula and see what you come up with. Okay, let's take a look. So barium, which is group 2, has a +2 charge. Oxygen, which is oxide, has a -2 charge from group 6. In this case, when we put together +2, -2, we are good to go. They balance each other out. BaO should be the correct formula. When we look at the next one, which is the aluminum, which is group 3, which is why it has a +3 charge. The sulfur, which is group 6, which means it has a -2 charge. When we put this together, we need to balance out this charge. So you want to kind of look for the common number that will do that. And if you're not sure, you can just multiply the two numbers together. So 3 times 2 is 6. So to get my aluminum to 6, I need not 1 aluminum ion, but I need 2 of them. +3 and +3 is +6. To get my sulfide or sulfur here to a -6 charge, I need not 1, not 2, but 3 of them right there. That's going to give me a -6. So now that I figured out how many I need, I just need to write what I did. So I have 2 aluminum. So when I write the formula, that means I put the 2 next to the aluminum. I have 3 sulfurs, which means I put the number next to the sulfur, again to the right of it, and we get Al2S3, which is aluminum sulfide. Lastly here, we have potassium, which is group 1, has a +1 charge. We have phosphorus, which is group 5, has a -3 charge. Once again, when we put this together, you can probably see what you need. You do need more of the potassium. You could also multiply it together. 1 times 3 is 3. So to get potassium to 3, I need 1, 2, and 3 of them. +1, +2, +3 to balance out the -3 charge. And all I have here is 1, 2, and 3 potassium. So when I write my formula, 3 potassiums, only 1 P, and we would have potassium phosphide. Again here, each of those things that are boxes, the sodium chloride, the aluminum sulfide, and the potassium phosphide, when they come together, and always when you put a metal and non-metal together, in terms of their formulas, they do have ions and they do have charges, and they should always equal 0. But the actual overall formula should never have a charge. But it is, again, important to remember that they are made up of these ions, which do have charges. All right, so I think that wraps up chapter 3 here. We've come to the end. See, not too long of a chapter. So we'll sign off for this one. We'll see you on the next one. Have a good day, night, or evening, whenever you're watching this, and have a good one.
Hello there. So it is time again for your favorite part of these lectures, which is chemistry joke time. Let me see here. A neutron walks into a sandwich shop and orders a submarine sandwich, and he asks how much does the sub cost. The person working there says, for you, no charge. Thank you.